These are two connected portals. It's easy to imagine how an object would pass through them. But what about if the blue portal comes into the orange one? Will this create a black hole? Or might the universe just return an error? Let's try it. Well, the universe is safe, and blue portal just comes out of itself. But there is something interesting going on. This is my solution to this problem, and in this video we will see what's inside of this, what a portal is, how portals can move, how it works, why there is no singularity, and what will happen to the object inside. My name is Ilya, let's dive in. For this video I wrote a program called Portal Explorer that draws portals using ray tracing. In Portal Explorer you can put portal into another portal and explore everything shown in this video by yourself. It even works on most smartphones. And there is a link to this program in the description. You are probably familiar with portals thanks to the Portal game, where they connect the same universe and can teleport light, unlike portals in many other works of fiction. After the game's release, the community came up with this question. And it's very hard to imagine a solution, because there are no portals in real life. We can't experiment with them and develop visual intuition. So please remember that this video is just a reasonable model that I explore via my simulation. Whenever this question comes up, people always say, portals can't be placed on moving surfaces. You really can't do this in the first game, but it is possible in the second game. Who is right? It doesn't matter. Let's not base our understanding of portals on some games. It's better to think of a portal as an abstract mathematical concept that can potentially exist in real life. Then our only limitation is rules of logic. Therefore, let's assume that portals can move until we run into contradictions. Let's first understand what a portal even is. There isn't a strict mathematical definition of them, only a vague idea of what a portal should be. I think that the portal concept comes from the idea of a doorway, which can connect two different rooms. We can build portals by cutting and joining space between doorways, like this. Now we can say that the doorway is just two back-to-back portals. This becomes our first property of a portal. If we connect two portals back-to-back to make a doorway, everything should work the same. Let's apply this property to the moving doorway. We see that the two portals that comprise it are moving too, and even if we move them slightly, nothing really changes. This also works for this kind of movement. As we can see, there's nothing preventing portals from moving. We've learned that portals can move while stationary relative to each other. Now let's consider another type of movement when only one portal moves. And we already have another community picture for this. I won't discuss it because it's just plain wrong as a question. It has no concrete values, speed, mass, force, everything. You can say that the object is very heavy and the portal is slow, therefore A is correct. Or the object is lightweight and the portal is fast, therefore B is correct. Everyone interprets this picture their own way. So I have plans to make a video about this situation with concrete values and with respect to energy and momentum conservation. So subscribe if you want to see this. For now, let's forget physics and talk only about geometry. This is a similar situation without gravity, air friction, conservation of energy or other physics. Here, the blue portal and object are still, but the orange portal moves and will fly onto the object. I claim that the teleported object will fly out from the blue portal, despite not moving before teleportation. Like this. And this is just visually appealing. But if you want an explanation, let's use the first property of portals. In a geometrical sense, a moving portal and stationary object is the same as a moving object and stationary portal. So if we connect backs of the portals, then the object should also move for the blue portal. So when portals move, they change the speed of anything going through them. Finally, since the portals can move, we can return to the original problem. To answer complex questions such as portal in portal, we must understand how a portal can teleport another portal at all. For that, we can take two independent pairs of portals, triangular and circular. Each has both parts, triangular here and circular here. Let's say that two different portal guns created them. So now we can take one triangular portal and push it inside the circular portal. The result is straightforward. Everything looks continuous and we can barely notice any change. But when the effect is so seamless, it's hard to understand how it works. So let's break the continuity illusion and disable light teleportation. Now our portals can teleport objects but can't teleport light. We see that there is some surface behind which is another place. We will use that frequently to understand how portals work. Here the red color represents the triangular portal part before teleportation, and the wall color has nothing to do with it. Next, the green color is after the teleportation. As a result, when we push the triangular portal inside, it splits into two pieces. We can see why the first portal splits, but why does this one split too? Why was it red, then half green, and then full green? Let's suppose that at this stage here, it must be not half red, but full red. What would happen then? We can understand that in the following scene. We can treat the missing part as green. It seems that everything is fine. When we move the teleported object up, it breaks on one side. This violates our first portal rule. When we connect the box, we don't get a clean doorway. It means that portals must always have the same shape on both sides. And therefore here, our portal is split into two pieces, red and green. When we teleport the input, the output will change its shape too. It might seem strange that changing one portal forces the other to change too, but it all makes sense when we remember that portals are created from a single doorway, and they are one thing that looks like two things. But if there are two portals, then why does this look so continuous? How does this work? Let's take a circular portal and split it into two pieces, red and green. It's split from both sides. There are many ways to split it. But if we turn on light teleportation, we will see that everything is continuous, despite the portal being cut into two pieces. Therefore, this division exists only in our minds, and there is no way to determine portal division by its appearance. We can divide any portal into infinitely many pieces, and this will be useful later. Now we understand that when two portals touch at their edges, then they can create a continuous image. In one case they touch physically, in another through a portal. We always push object into a whole portal, so how should we handle a split portal? If we move this square object, it will look like this. But how must that work in the implementation? If one object enters two different portals, then there must be two different objects on the other side. The green portal creates a green copy and the red portal creates a red copy. We can do that by placing an imaginary knife on the portal borders. This knife will cut an object along its speed direction, resulting in separate objects entering their own portal. An object is cut on the input, but it will be joined on the output, and portals always work this way. There is no way to determine when an object is being cut, so this knife exists only in our minds. Now we have a clear picture of that scene, and this is very important, because that's the whole point. In the portal-in-portal problem, nothing teleports by itself. Every portal is teleported by another portal. Our job is to split the portal into independent pieces, thereby we get rid of paradoxes and turn an impossible task into a computational one. But before continuing further explanation, let's return to the start of the video and better figure out what is happening. The first thing to notice that portal is moved to the edge. This border prevents it from moving further. Then we should see that the blue portal comes out from the blue portal. In other words, it comes out of itself. So one picture about the portal-in-portal problem that I found on the internet is wrong. Colors do not alternate. Then, what if we look inside? We see an exciting recursion pattern from the blue portal and the same image from the orange portal. Such recursion isn't strange because we see similar effects with standard portals. Due to that recursion, everyone thinks that we have some sort of singularity here. But actually we don't. Everything works like regular portals, and I will show that by placing an object here. An object can be there without touching anything, with no singularities yet. If we push it into the portal, it just teleported to a different place. It will not duplicate, sometimes splitting into three parts. But if we enable light teleportation, it will look like the object isn't teleported anywhere, not even cut. And the distance between the object and its images is preserved, just like with regular portals. So there is no singularity. If we disable light teleportation, we will see colors, red, green and blue. We already saw this in the previous scene, with red and green colors. Here these colors represent the same thing. The red color represents the non-teleported part, the green color represents the first outgoing part, and blue represents the second outgoing part. These colors represent teleportation degree. how many times that portal section has been teleported. Red represents first degree, green second degree, and blue third degree. There are infinitely many degrees represented by other colors. For example, there is fourth yellow degree for this setup. When one portal comes into another, the degree of an incoming portal and degree of receiving portal add up into an outgoing portal. This happens because of how portals work mathematically. But this video will be too long with the math explanation. Write a comment if you want portal math analysis. To get a green portal, we need to put a red portal into the red portal. To get a blue portal, we can put red into green or green into red. There are many ways to get a yellow degree. And for the end of this section, let's just look at beautiful rotations of portal inside itself. If we pause this animation, we will see this beautiful picture. See how many teleportation degrees there are. Okay, it's all clear now, but how do we unite all this magic and make it work? If you worked with physics simulation or game development, then a naive solution is obvious. We need to take discrete steps and make a procedure that will return the next simulation step from the current one. This is how we will make a discrete approach. We have this scene where the object has come into the portal in one discrete step. By the end of this step, we can cut the entered part entirely. If previously we cut by the speed of an incoming object, then now we have a second cut approach, cutting along the portal surface. And we see that we have two different parts. One fully enters the portal and the other doesn't enter at all. And we can teleport this second part. This is how teleportation looks. Move, cut, return, teleport, move again. We can imagine something like that for portal teleportation. Now we have all the pieces to create a discrete approach. I spent months programming this a long time ago, before Portal Explorer. Here colors are different because of a different algorithm, but the main idea is preserved. We have some state, let's continue with it. First, we find where to cut, like we did previously, cutting by portal plane. Notice when we cut the blue portal, a seam appears on the orange portal too. Now move and teleport. And now join parts with the same color, which is physically near. This is needed to save computational resources. Now cut by portal plane again. And here we have a new stage, cutting by speed knife. We see that this little piece is cut exactly by this type of cutting. Previously we had two different portals nearby too, and the border between these parts creates a speed knife. And now look, if we cut the incoming portal by these borders, and these borders emerge from cutting, then we have a recursion, and cutting process might continue indefinitely. Fortunately, this doesn't work like that, and this process will stop. In this scene we got fortunate because there is a small number of parts, but for other setups this can work badly. Do you remember I said that every portal is teleported by another independent portal? So this is the essence of the discrete approach. We cut a portal into pieces until we have each portal teleported by another independent portal to get rid of paradoxes. This is the reduction of an impossible task to a computational one. Everything works like that further in that scene. The problem is fully solved for flat portals. But for complicated non-flat portals, my code mostly worked, albeit with strange bugs that I haven't figured out yet. Let's try to put this complicated portal into another part of it. At first everything works fine, but then some triangles appear. This is the bug. Because of that I call this approach naive, because it's easy to invent but it's ineffective and difficult to implement. This led me to believe that I am doing something wrong, and there should be a much simpler way. And I managed to invent such a method, but a bit accidentally. I call this the analytical approach. I will start by explaining it on an object and then transfer this to portals. First we will learn how to teleport a triangle. The triangle is defined by its coordinate system. This coordinate system determines the plane for the x and y axis, in which the triangle is located. The blue axis is z, the normal axis to that plane. The triangle remains fixed in that coordinate system. Therefore, to move the triangle, we need to move its coordinate system. Similarly, portals are just planes determined by two coordinate systems. And there is an operation called teleportation, which takes three coordinate systems and returns another coordinate system. Here x represents the triangle coordinate system and P1 and P2 are the coordinate systems of the portals. In the interface, this coordinate system is created this way. So teleported coordinate system will be placed behind blue portal. And if we move the triangle, this coordinate system will move too. So we can replace that coordinate system with second triangle. And when moved, the triangle looks like it comes out from the blue portal. Let's push this triangle by half. If we disable the other triangle, then we will see only one useful part of the first triangle. The other part does nothing useful and must be removed. But if we disable the first triangle and enable the second, we will see the same but inverted. But if we enable both parts, it will look like our teleportation works but with two excess parts. So we need to get rid of them. And here we need to pause for a moment. In this program I use ray tracing to draw everything. For example, let's draw a circle. To do this, we write a function that takes an arbitrary point on the plane, determines if it lies within the circle, and returns a material number that defines how that point should be painted. Therefore, if we want to filter something, we can do this for each point independently. For example, we can get a circle by writing that the distance must be lower than 1, just like in the high school definition of a circle. Now, how to get rid of excess parts? Remember that portals are just planes. The useful part is located in the positive half of the z-axis, and the excess part is located in the negative part of the z-axis. Then we can add this code to filter excess points. In this code, we transform the current point on a triangle surface into orange portal local coordinates, and then if the z part is negative, then we remove that point from the painting. This removes the extra part. We will do the same thing for the other triangle. And now triangle teleportation looks correct. Let's think about what happened. We have two triangles, and we can say that they are two teleportation degrees of the triangle, first and second, and we just filter which part is visible and which is not. But this isn't a perfect solution, because we filter incoming objects by unbounded planes, and not by portal surface. So the key idea of an analytical approach is add as many teleportation degrees as needed, then filter excess parts. And this is enough to solve the portal-in-portal problem. Here everything works the same way. We have some number of teleportation degrees, and we filter excess parts a little smarter. But here the code is more complicated. First, we have code to transform coordinates of the orange portal, and then we have code to filter by planes. The code is big for the 11th degree because we must filter by 10 previous portals. I use only 11 teleportation degrees, I can do more, but in most cases this isn't necessary. This is how all 11 teleportation degrees looks without filtration. And they are looking very cool when rotating together. This is how the analytical approach works. And it's better than the discrete approach, but it has pros and cons. Cons, it works only for ray tracing. Therefore, we need a lot of computational resources. We have to write each teleportation degree by hand, in code. It works only at the visualization stage. That is, to put physics here, we need to reinvent everything. Pros, it can be programmed very easily. Therefore, it's less prone to errors. It works very well for demonstration purposes, which is what I'm pursuing in the first place. By the way, I have an idea how to solve the problem of the unbounded planes, but this is the topic for another video. To solve this video's problem, I wrote a discrete approach for months. It was really hard and tedious. But with this analytical approach, I made the portal-in-portal just in one day. And from this example, I am more convinced that it is more important to learn how to find effective and clever solutions, instead of being diligent in solving naively for a long time. Okay, now what you definitely want to know. As I said, here the portal can be moved further than that. I'm sure that you are interested in what will happen if we move the portal further, ignoring these limitations. There were no unbounded planes in my old code, so thanks to it we can see what will happen. Previously we stopped here. Okay, we move forward and see that the portal is being cut parallel to its velocity. This occurs because the speed knife exists not only between portals, but also on the borders. Now this portal breaks here. On the orange portal these parts are located nearby, but for the blue portal they are placed far from each other. Therefore here we have a deadly knife. If we look at this scene with light teleportation, then it will look like that. Sorry about this rough visualization, the old program can't do better. As I said, to solve the problem of this video I wrote this program, where you can see and create portal scenes. And every scene that I showed in this video is in this program. In scenes you can tweak different parameters. This program has many windows for users. This is the most important. Here you can control the current scene or read a detailed description about it. This program also has camera and rendering settings. For example, you can enable Panini projection or increase anti-aliasing. And the next window is most important for me. I can edit a scene here, and you can too if you want. And a couple of words about the technical details. As I said, everything is drawn by ray tracing. It works on GPU through shaders. Shaders are automatically generated using available objects. Matrices and sliders are transmitted by uniforms. Uniforms can be sent in real time, which is very convenient to create real-time movement. The whole thing was written in pure Rust, my favorite programming language. The interface is made using the concept of an immediate mode GUI. I didn't expect that I could make all that so fast. For this type of interface I used the eGUI library. This program works not only in the browser, but also on Windows, Linux and macOS, thanks to the MacroQuad library. And in the browser this works not because it's written in JavaScript, but because Rust can be compiled to WebAssembly, which can run in browsers. The source code of this program is available on my GitHub. I have many more portals of different complexity and many more paradoxes and questions. So don't forget to subscribe. That's all, bye!